started.
Hello, this is Dr. Leslie Ann Asmus, and in this recording session, I'm going to continue along the discussion of hypothesis testing. In the previous one, I was talking about hypothesis testing from a standpoint of parameters of different distributions. And so, did hypothesis testing about what's the probability, or with a null hypothesis, that the average household income was a certain number, 50,000. And the alternative hypothesis would be something like the average household income is greater than 50,000. We looked at a couple of examples with regard to proportions and saying, okay, I will use my sample information to test a null hypothesis that the probability of success out of a binomial distribution is equal to 0.80. And an alternative might be that it is not equal to 0.80. And so in this session, we're going to look at a hypothesis testing of a form called goodness of fit, as well as using hypothesis testing in the area of independence. So goodness of fit test. Do actual population characteristics fit the hypothesized distribution? So I've said this a number of times in class and possibly in these recording sessions about, we're in kind of a very clean and just tidy area being in the academic, and the textbook exercises tend to be very neatly defined. Your exercises at the back of the chapter are pretty much focused on the concepts and the introduction of different things that were contained in that chapter. So at the end of the section on binomial distribution, you had a bunch of exercises related to binomial distribution. At the end of the section related to the exponential distribution, probability distribution functions, you had a number of exercises related to those. But in the real world, in the whatever company or organization you're working with, if you go in and you have to do a statistical analysis, a lot of times that analysis is look at existing data, look at historical data, go out and gather some data to answer some business or engineering questions. So what is the average arrival rate of people to an emergency care center? What is the probability distribution function associated with good parts coming off of a manufacturing line or machine? So you have these real engineering challenges and questions, and you might gather your data, you might gather some information, and then make a hypothesis about, well, the probability distribution function I assume to look like this. And therefore, off of that, I can determine some values of the expected values. I can determine the standard deviations. I can do that based on a hypothesis of what the distribution is. And so what goodness of fit does is it says, well, do your population characteristics actually fit to what you've hypothesized about that distribution? And you'd expect to, if it truly is the distribution you think it is, you'd expect samples to come back supporting that with frequencies and such supporting it. So how do you then go back? And again, think about it. Suppose somebody 10 years ago or even 12 months ago said, this is the distribution. Probability of success is 0.80, follows a binomial distribution, probability of success 0.80, and for whatever, a manufacturing line or something like this. And today you're asked the same question, well, is it still binomial? Does it still have a probability of success P equal to 0.80? And so what you do is you're going to go out and gather a sample, look at the observations of that sample against what you would have expected them to be based on your assumed or hypothesized distribution. How big can the discrepancies be before you question your hypothesis or beliefs about the population? So when you look at this kind of goodness of fit test statistic, or test in general, you have a sample size of size K, and the goodness of fit test statistic goes back to a chi-square. And what you're going to do is, based on a presumed distribution, you could go and figure out what would be the expected frequencies, what would be the expected values for a sample of size K. You can figure out what those are. And then you can compare that to K observations that you have and the difference between those two. And so that's what this chi-square test statistic is doing. As you see, you sum from 1 to K, the observed value, O sub I, minus the expected value, E sub I, square that difference, divide by E. And this is going to follow a chi-square distribution, as I've discussed in the recording session. Believe it was with regard to sampling distributions for a sample variance. Okay, so we're back with the chi-square distribution. In this case, our degrees of freedom, again, are the sample size, K minus 1, degrees of freedom. And the O sub I are the K sample observations, while the E sub I are the K expected values that are generated on the basis of your hypothesized distribution. Okay, so this again, here we go. So what's your test? You basically go out, draw your sample, size K, calculate your chi-square test statistic. You have, just like we did before with the hypothesis testing, you have a level of significance specified, alpha, and you go and you can look up on a table or you can look online, values associated with the chi-square for alpha. What is that number? And then you could compare your sample results against that chi-square with this identified for the alpha level of significance. Then decide whether you're going to reject H naught, which is H naught would be your null hypothesis would be that your hypothesized distribution is this and such, and the alternative would be that it's not that distribution. And so you're using, again, the sample results to identify whether or not your hypothesized distribution is truly what you have to work with. Again, boy, I'm just like blasting through this topic. But you do have some textbook exercises you can work on. When we get together in class, we'll go through this and talk about it a little bit more with some pictures and that kind of thing as we go through more examples in class. But this is a first brush into the idea of, okay, so what is goodness of fit? Let's look at another type of statistical hypothesis testing, and that is for testing for independence, particularly for categorical data. Okay, so trying to link some of these things together. Recall the joint probability distribution when we looked at joint behavior of two random variables, and we identified that independence in general is if you have the case that probability of event A and B is equal to the product of the two probabilities, probability A times the probability of B. Now we test the hypothesis of independence between two variables of classification. So these are I thought these were some good examples. Are the voters' ages and candidate preferences independent? Are the types of crimes and the day of the week independent? Are hurricane intensity and duration since landfall independent? Are supplier manufacturing facilities and lifespan of component independent? Where you make something, is that independent of how long it's lasting? The durability of it. And so this kind of question, this test for independence comes up, as you can imagine, quite a bit in actual applications. So just kind of a few of the elements of terminology in this arena. And it goes back, and you see this is the same data we had before with the National Transportation Board, Safety Board. Using observed sample values, you could create a contingency table with R rows and C columns. So our joint distribution that we had previously, we had, excuse me, 3 rows.